Good evening. My name is Carlos Hermoso from University of Alcalá, and this is a joint work with Edmundo Huertas and Alberto Lastra, both from University of Alcalá, and Anier Soria Lorente from University of Granma. This is the title of my talk, Analytics Results on Discrete Solet Type Alsalan-Karlich 1 polynomials involving an arbitrary number of Q derivatives. This is the outline of the talk. The talk consists of 3 sections. In the first section, we are going to give a little bit of history. We are going to remember what is the meaning of what Alsalan-Karlich polynomials are, a brief review of Q-calculus, what are Sobolev orthogonal polynomials. And in the second section, we are going to introduce our new family of polynomials, Alsalan-Karlich 1 Sobolev type. We will introduce this monic polynomial orthogonal sequence. We will state several connection formulas. We will see the hypergeometric representations of this new family. We will state structure relations, ladder operators, and finally, we will state 3-term recurrence relations and several versions of holonomic equations that this new family satisfy. The talk ends with some examples of the genus family. And now the introduction. Well, what are Alsalan-Karlich polynomials? Alsalan-Karlich polynomials of 1I2 were introduced by Walid Al-Salam and Leonard Karlich in this reference here, some orthogonal Q polynomials in Mathematische Nachrichten, and were introduced by means of the Brenke-type generating functions. That these generating functions is this expression here. And the Alsalan-Karlich 1 polynomials 1 are the coefficients of the expansions in power series of this expression here, and these are the Alsalan-Karlich 1 polynomials, and the expansion of these expression here. The expansion by means of power series, the coefficients are the Alsalan-Karlich polynomials too. Well, we will see later, although it's very well known, this symbol is the Pochheimer symbol. Alsalan-Karlich 1 and 2 polynomials can be expressed by means of hypergeometric series. This is the hypergeometric function 2 phi1 or phi2 and phi2 0 for the Alsalan-Karlich 2 polynomials. And these two families of polynomials are related, and the relationship is very well known. For example, in Chihara book, these relations for these two family of polynomials. Why are interested to study Alsalan-Karlich polynomials? Alsalan-Karlich polynomials appear in mathematical physics, especially in quantum mechanics. We can find Alsalan-Karlich 1 polynomials in Q-harmonic oscillators, and many properties of these Q oscillators can be obtained by means of properties of the Alsalan-Karlich 1 orthogonal polynomials. We have here some reference of the use of Alsalan-Karlich polynomials in quantum mechanics. And we are going to remember basic definitions and properties. All these definitions and properties are very well known, but we will need these properties in the sequel. Well, we start with the Q number, the very well-known Q number. The Q number is the sum of all the powers. We'll express the Q number in this way, and is the sum of the powers of Q, Q power to starting from K equals to 0 to K equals to N minus 1. It is the sum of all these increasing powers. We also have this very well-known equality, this very well-known limit. We have the Q analog of the factorial of n defined in this way here. And we have the Q analog of the Pochhammer symbol of sigma factorial. That is, this is product 1 minus a by 1 minus aq by 1 minus aq power to 2 and dots 1 minus aq power to n minus 1. This is the shifted factorial. And we will use the usual notation, the following notation, this. And we have the Q hypergeometric series phi rs defined in this way. The hypergeometric function phi rs is defined in this way, in this expression here. And we also have the Q analog of the binomial coefficient. The Q binomial coefficient defines like this. And we have the Q derivative operator and the iteration of this operator. The operator, the Q operator upper n is the iteration of n times the Q difference operator. And of course, the limits when Q tends as 1 is the derivative. Well, we present here these properties because we will need in the sequence. We also have these properties, the usual properties. We can find these properties and the proofs in this, for example, in this reference here. And we have the Q analog of Leibniz rule. That is this expression. And we also have a Q-Taylor formula that is this expression here. And to state this Q-Taylor formula, we need the Q subtraction operator that is defined in this way. All these properties are very well known. And now we are in position to define Alcalá-Carlich 1 polynomials by means of an inner product. And Alcalá-Carlich polynomials, this is the family, are the family of polynomial orthogonal with respect to the inner product defined by means of these measures, these continuum measures, that this measure has jumps at the points x equals to the power of q power to k when polynomial satisfying this orthogonality relation. This is these expressions here. Well, properties for the Alcalá-Carlich 1 polynomials. All properties are very well known. The recurrence relation or the structure relation, the norm, the squared norm. We have the shift operator, the forward shift operator, this is the Q-following factorial. We also have the second order Q difference equation that these Alcalá-Carlet polynomials satisfy. And we have the expression of the coefficients of the equation. We can also define the kernel. We have the nth reproducing kernel defined in the usual way, and we also have a Christoffel-Darboux formula. We will denote in this way KNQ upper IJ. We denote in this way the derivative, the Q derivative in variable y of order I of the derivative, the Q derivative in variable x of order j of the n reproducing kernel, of the nth kernel. And this is the expressions. This is this is the notation. And now we have the first technical lemma. Well, we have a shadow in this box. I don't know what's happening, but well, these formulas are very. We can see very well the formulas. This is not a problem. This is the first lemma, the first technical lemma. If this is the Alcalá-Carlet 1 polynomials, we have an expressions for the derivative of order j in variable y of the n-1 kernel, and relating this derivative relating to two consecutive Alcalá-Carlet 1 polynomials of degree n and n-1. This is a technical lemma where this an and bn are these coefficients. These coefficients present these expressions here. And this lemma, we will use this lemma afterwards. And now, what are sobel-orthogonal polynomials? Sobel-orthogonal polynomials are families of polynomials orthogonal with respect to inner products involving regular derivatives. When these derivatives appear on a finite discrete set, these families are called Sobolev type or discrete Sobolev-orthogonal polynomials sequence. Bavinck, in this reference here, introduced by the first time inner products involving difference instead of regular derivatives. By analogy, we also call these families Sobolev type or discrete Sobolev inner products. Well, this talk is based of this reference here on second order Q difference equations satisfied by Alcalá-Carlet 1 Sobolev type polynomials of higher orders. By these authors, Edmundo Huertas, Alberto Lastra, and Daniel Soria, and in this paper, we will deal with monic polynomials orthogonal with respect to a Sobolev type inner product related to the Alcalá-Carlet 1 polynomials and involving an arbitrary number j of Q derivatives. And the main purpose of the work is to provide several versions of connection formulas, structure relations, ladder operators, second order Q difference equations, all these expressions for this new family. We study all this new family, and we state all the relations and equation for this new family. And another contributions is a three-term recurrent relations with rational coefficients for this new family. And now This is the second section of the talk, that is the introduction of the new family of Alcalá-Carlich one-over type polynomials, and all these formulas, connection formulas, and holonomic equations. Well, we will denote in this way the monic orthogonal polynomial sequence with respect to this overlap type inner product. Observe that in this expression here, this is the measure, the continuous measure of the Alcalá-Carlich 1 polynomials. Lambda and mu are two bases, and this correct part involves q derivative of order j, located in a point A, and one outside of the support of the measure, in the front the support of the measure. And of course, this expression here denotes the q derivative operator. Well, the monic orthogonal polynomial sequence associated to this inner product is the Alcalá-Carlich 1 type polynomials. We are going to state the first connection formula for this new family we have obtained. And now, expanding this family in terms of the Alcalá-Carlich polynomials, we have these expressions here. And this is these coefficients of the expansions are unknowns we have to determine. In the expression of the coefficients, the q derivatives of order j appear of this family that are also unknowns. Well, using reproducing kernels, we can express the previous formula by means of these kernels. And recall these expressions have appeared in the technical lemma we have also stated previously. And now, changing x by the value of a, we have an equation, and also change x by 1, we have another equations, and we can obtain a linear systems where the unknowns are the q derivatives of order j of this new family. This is the matrix of coefficients, and this is the column of unknowns. Using Cramer's rule, we can obtain the expressions we can obtain the expressions of the derivatives, and we also have the coefficients, and we have the expression of the Alcalá-Carlich 1 type polynomials in this way, in terms of the n-1 kernels. The q derivatives of order j of the n-1 kernels. Then, using the previous formula, the previous and the lemma, and the technical lemma we have stated previously, we can obtain an expressions, the first connection formula, that is this formula here, that allows to relate Alcalá-Carlich type polynomials of degree n to two consecutive Alcalá-Carlich 1, the classic family, the old family polynomials of degree n and n-1, and we have the expression of the coefficients here, c1n and d1n. And now we are going to state another connection formula, the connection formula 2. Using connection formula 1 and the recurrence relation, we also have another connection formula, but now for the Alcalá-Carlich 1 Sobolev type polynomials of degree not n but n minus 1. And this is a connection formula that that allows to relate Alcalá-Carlich polynomials of degree n minus 1 to two consecutive Alcalá-Carlich polynomials of degree 1 of degree n and degree n minus 1. And this is the expression C2n and D2n of the coefficients. We also have connection formula 3 and 4, but now relating Alcalá-Carlich Sobolev type polynomials to two consecutive Alcalá-Carlich old polynomials consecutive of degree n and minus 1, but Alcalá-Carlich polynomials of degree n's two consecutive new polynomials, Alcalá-Carlich Sobolev type polynomials, one Sobolev type of degree n and n minus 1. And we also have two connection formulas, 3 and 4, for Alcalá-Carlich 1 polynomials of degree n and degree n minus 1. We have the expression of the coefficients C1n, C2n, D1n, and D2n. We have the hypergeometric representation. By using the hypergeometric representation of Alcalá-Carlich 1 polynomials, we also have the hypergeometric representation of Alcalá-Carlich Sobolev type, Alcalá-Carlich 1 Sobolev type polynomials. And this is the expressions here. And now we can state structure relations. Well, we have these two structure relations. In fact, one structure relation for the q power L derivative of Alcalá-Carlich Sobolev type, Alcalá-Carlich 1 Sobolev type polynomials of degree n and Alcalá-Carlich 1 Sobolev type polynomials of degree n minus 1, but we have not two structure relation, but four structure relations. Two relations of the like the first one for L equals to minus 1, and and another one for L equals to 1. We have four relations. Two for L equals to minus 1, and another two for L equals to 1. Well, this is the expressions of all the coefficients that have appeared in formula in previous formula. And we also have this starting from the connection formula 04 and the previous lemma, we also have these structure relations. Observe that we also have four structure relations for L equals minus 1 and for L equals 1. And now we are state ladder operators. Ladder operators, we have the destructions of lowering operator and the rising and creation operators, and this is an expression for these operators. This is the lowering operator and this is the rising operator. Ladder operator verified that lowering operator acting of Alcalá-Carlich 1 polynomials Sobolev type of degree n yields Alcalá-Carlich polynomials 1 subtype of degree n-1, and rising operator or creation operator acting of polynomials of degree n-1 yields polynomials of degree n. We also have two rising operator and two lowering operators, one for L equals to -1, and again another one for L equals to 1. Well, an application of the formal use of ladder operator is the recurrence formulas. And recall that we also have not one recurrence formulas, but two. One formula for each value of L, -1 and 1. We have these two three-term recurrence formulas when this is expressions of coefficients. And another we also use ladder operator to attain the second order holonomic equation. Well, the first version of the second order holonomic equation can be obtained by means of the action of the ladder operator, acting the lowering operator of Alcalá 1 subtype polynomials of degree n, and after acting the actions of the rising operator, we obtain and rearrange in terms the second order holonomic equations. That is this equation in this way. Observe that we have not one second holonomic equation, but two holonomic equations for L equals -1 and 1. And we can also obtain when these are the expressions of all the coefficients. And we can also obtain another version of the second order holonomic equation, but now not acting ladder operators, but acting q-derivative operators. Acting the q-derivative operator and the q and power -1 derivative operator in the same way that ladder operator, we can also obtain another version of the second order holonomic equations. That is, this is expressions here, right? This is what this is the expression. Well, this in this box, this is the first line. This is the expression of the second order or the second version of the second order holonomic equation. And finally, some examples. Well, in this picture, we have three polynomials, Alcalá 1 subtype polynomials of degree 0, 1, 2, and 3. And this is the expression of this polynomial here. Well, q is the value of q is 0.5, and we also have, well, we have these polynomials involving the q derivative of order 2. And another example involving derivatives of order j equals to 3, three polynomials, so there is 0, 1, 2, and 3. And we have this picture for these polynomials. Finally, we have several references, and thank you very much. This is all. Thank you very much.